Light is the fastest traveler the universe has ever known. Every photon that has ever left a star or a distant quasar has obeyed a rule so strict that even the deepest gravity wells cannot break it. The speed of light in a vacuum is not merely fast, it is absolute. Not approximately absolute or usually absolute. It is a law that refuses negotiation. Even the strongest gravitational fields cannot change what light is locally capable of. The cosmos speaks one unwavering command. A light beam must always move at the same speed when measured in its immediate surroundings. Imagine you hold a flashlight in your hand while floating far from planets or stars. You flick it on and watch photons rush outward. If someone else is speeding away from you in a spacecraft traveling at 99.99% of the speed of light, and they turn on their own flashlight, the light from both flashlights still races forward at the same ultimate cosmic speed. The universe never allows a different answer. You can run toward the beam or away from it. The beam does not care. It does not go faster for the one charging forward. It does not slow down for the one racing ahead. The measurement for each observer will always give the exact same value for the speed of light. This rule sounded impossible when Einstein first dared to believe it. How could motion not change speed the way it changes with every other object we know? Cars add their speed to the road. Spacecraft add their speed to the vacuum. Throw a ball forward in a moving train, and the ball definitely gains the train speed plus your throw. But photons are different. Photons ignore the train. The cosmos bends itself to preserve the speed of light. To protect that cosmic constant, the universe must bend something else. Space and time themselves must change depending on how you move. Einstein realized that if the speed of light is always identical for every observer, regardless of their motion, then distances and durations cannot be absolute. They become elastic. They stretch and shrink to make sure the rule holds. This is where the world you think you know begins to unravel. The ground beneath your assumptions becomes soft. Time can slow down for a fast traveler. Space can contract in the direction of motion. These changes are not illusions. They are measurable. They are real. This is how the cosmos preserves its most sacred limit. The reason this is so important is that light defines what is possible. Information can never travel faster than a photon. Causality, the essential ordering of events, depends on that speed limit. If light did not have a constant speed, communication could become chaotic. One observer could learn an effect before its cause. The structure of logic could collapse. The universe would not just feel strange, it would not function. Yet there is a deeper layer of mystery beneath this familiar statement, that light is constant. We must focus on one crucial word: locally. Light always travels at the speed of light in its local environment. But what does local mean when the universe is warped by gravity? A photon passing near a massive planet or the bright and scorching star we call the sun might appear slower from a distant vantage point. Our instruments might detect that its journey took slightly longer than expected. Scientists once debated whether gravity actually slows light itself, but the truth, when examined through the lens of general relativity, is more surprising. Gravity can slow clocks. It can stretch the fabric distances are measured across. The rule that light is constant still holds, but the rulers and the ticking seconds change in the presence of mass. If you were hovering close to the surface of our sun, with a perfect laboratory of mirrors and detectors, you would still measure a beam of light racing at the same speed as always. Meanwhile, a distant astronomer watching your region from far away would see everything unfold more slowly. The clocks near the sun appear to tick slower than those far away from its pull. Space itself is not the same from place to place. The cosmic playing field is curved, yet the players never break the rule. This difference between local truth and distant perception will soon become the heart of our journey. When scientists in the 20th century first bounced radar signals near the sun and detected that the returning light took longer than expected, they did not discover a defeat of Einstein law. They discovered its final confirmation. Light was moving through a warped map of space and time. What seemed like a slow trip was really the universe making the distance longer than Euclid ever imagined. The speed of light remains the most stubborn constant in physics. But the arena where it moves is not rigid. That is the secret that forces us to rethink everything. When gravity enters the story, distances and durations reshape themselves. What you think of as slowing down is only the universe changing what the words speed and distance mean under its influence. To understand this fully, we cannot cling to everyday experience. When you walk across a room, the floor does not stretch. Your heartbeat does not slow because the wall pulls on time. But on a cosmic scale, gravity is not a simple pull. It is geometry in motion. Light does not change, reality does. This chapter will show how the constancy of light forces the universe to be dynamic, not static. We will learn why believing that light slows in gravity is a misunderstanding created by a human need for familiar ground. Our clocks and our rulers betray us near massive objects. Light remains perfect. We are the ones who distort. The rule is iron. Light does not hesitate. Light does not compromise. There is only one speed it can ever have in empty space, in every corner of the cosmos, no matter how deeply gravity has curved that region. We stand at the edge of a revelation. If the speed of light cannot change, then something fundamental about motion and attraction must be reimagined. When we let go of the old idea that gravity is a force pulling objects together, the truth of curved spacetime emerges. That is where our story must go next. Light carries the history of the universe across unimaginable distances. It rushes from galaxies so far away that the vast stretches of space between us have been expanding during the entire journey. Yet even across these cosmic realms, even after millions or billions of years of travel, every photon still obeys that same unwavering command. Move at the exact same speed when measured in your local surroundings. The universe enforces this as if everything depended on it, and everything does. To understand why this matters, picture yourself drifting in the darkness of interstellar space. There is no up or down, no sound, no wind, only the quiet pulse of distant stars. You hold a small device in your hand that emits a brief flash of light. As the beam streams outward, it defines a boundary between what can happen and what cannot. Nothing carrying information can break through that frontier. The speed of light marks the ultimate connection between events. If something outran those photons, it could allow communication backward in time. It could shatter cause and effect. The universe protects causality by declaring that nothing outruns light. This truth becomes even more profound when we consider how light interacts with motion. Suppose another observer speeds past in a gleaming spacecraft, traveling at a tremendous fraction of the speed of light. They too measure the beam and find its speed unchanged. Time itself slows for them. Space stretches. Their entire reference frame reshapes to preserve the rule. The speeds do not combine. The math of ordinary experience collapses. A deeper geometry takes its place. Einstein's extraordinary leap was recognizing that the speed of light is not simply a property of photons, it is a property of space-time itself. Light is the messenger that reveals the blueprint of the universe. When its behavior looks strange, it is really the structure of reality transforming beneath it. The key to everything lies in measurement. Speed is always distance divided by time. Both distance and time are usually treated like universal facts, identical for everyone everywhere. That turns out to be wrong. Time flows differently depending on your motion and the strength of the gravitational field around you. Distance itself changes shape near mass or energy. The idea that rulers are rigid and clocks are faithful only applies in the gentle environments we evolve to survive in. From our everyday point of view, this sounds absurd. How can time be different for two observers? How can a meter not always be a meter? But these are human inventions attempting to measure a universe that cares nothing for our tools. When we travel fast, our seconds stretch. When we stand near a massive object, our seconds slow compared to someone far away. Not because of illusion, because of geometry. This is why scientists emphasize the word local. Locally, meaning in your immediate vicinity, where space and time share your same curvature, the laws of physics retain their simple form. Light always travels at the same speed when measured by a nearby observer whose clocks and rulers exist in the same gravitational conditions. But when that measurement is compared across different regions of curvature, it no longer matches. What changes is not the photon behavior, but the comparison between different patches of space-time. Imagine a beam of light traveling near the edge of a giant star. An astronomer far from that star might send a signal that passes deep into the star gravitational well and then reflects back. When she calculates the duration of the journey, the round trip takes longer than Newton or Euclid would predict. Something seems to be slowing the light. But a scientist close to the star would measure every step of that journey and find nothing unusual. The delay only exists between observers standing in different gravitational environments. The difference is like drawing a straight line on a curved map and insisting that length should equal the flat world expectation. When the surface itself curves, the path is no longer what it seemed. The universe has its own definition of straightness and shortest distance. Light always follows the straightest possible path through space-time, but straight itself becomes curved by gravity. All of this leads us toward an extraordinary conclusion. The speed of light is constant, but the meaning of distance and time is not. When gravity strengthens, clocks slow down. They slow because time itself passes differently. Distances stretch. They stretch because space itself is warped. These effects do not depend on machinery quirks. They are measured with atomic precision. Our best instruments have already seen these distortions. On Earth, clocks placed just a few floors higher in a building tick faster than clocks on the ground. The difference is tiny, but undeniable. Astronauts aboard space stations age slightly more quickly than people on the surface below. Gravity shapes reality, even in the world we think of as normal. So what is the speed of light revealing? It is revealing the true architecture of the universe. Not a rigid stage where events happen, but a living geometry that responds to mass and energy. If you insist on treating distance as fixed, you might conclude that light slows in gravity. But gravity is not forcing the photon to hesitate. It is reshaping the terrain the photon crosses. The rule that photons must obey is far more resilient than any law humanity has ever written. Light always travels at the same speed when measured in the same local conditions. If those conditions change from one place to another, the measurement changes too. But the photon remains faithful to the deeper structure of relativity. The fascination grows even stronger when we ask, what happens at the edge of an extreme gravitational field, such as the boundary surrounding a black hole? From a distant vantage point, light appears to slow to a crawl as it approaches the event horizon. Eventually, it seems to freeze, suspended in time. But from the viewpoint of the photon, nothing unusual occurs. The local speed remains the same. The perception of slowing belongs entirely to the distant observer who is comparing clocks that no longer agree. This difference between local truth and distant interpretation is not a loophole. It is the essence of Einstein theory. It allows light to remain the unbroken standard against which all motion is judged. It prevents contradictions and preserves causality. It keeps the universe sane. We have begun to see that the constancy of light is both a boundary and a doorway. It forces us to accept that our intuitions about motion are limited by our small corner of the cosmos. It guides us toward a deeper understanding of gravity that does not involve forces pulling on objects, but geometry guiding them along curved paths. Yet the most surprising pieces of this story still wait ahead. If gravity is geometry, and if light always follows that geometry perfectly, then the illusion of light slowing down is only the start of a far stranger truth. Gravity does not tug on photons. It reshapes the stage beneath them. Light reveals the warping that gravity creates, bending not just paths, but the flow of time. Every idea we hold about motion is shaped by our own fragile human scale. We walk, we run, we ride machines that push us faster, and we assume speed adds and subtracts like coins in a pocket. Yet, the cosmos refuses to honor such simplicity. When the speed of light remains unchanged for every observer, no matter how fast they move, our comfortable arithmetic breaks. The universe reveals that our intuition is provincial, tied to slow lives lived on a small world with gentle gravity. Light is the reminder that reality is deeper than instinct. To truly appreciate what the speed of light means, imagine traveling beside a photon. Though in truth this is impossible because no massive object can ever reach that speed. Still, picture the journey in your mind. If you could ride alongside a beam as it moves, you might expect the photon to appear still, like a companion sitting beside you. But the universe blocks this idea entirely. There is no rest frame for light. It is always in motion. Its speed is not just fast, it is fundamental. It shapes the fabric of causality itself. Events connect only if light has enough time to bridge them. If something outran light, the consequence could precede the cause. The arrow of time would be lost. This is why scientists treat light as the reference for everything. The speed of light writes the rules that spacetime must obey. It is the heartbeat of relativity. Yet this heartbeat has strange rhythms once gravity enters the picture. Imagine a massive planet bending the space around it. A photon glides through that curvature. To the photon, nothing unusual occurs. It moves with its constant speed through its local surroundings. But to a distant observer who measures the journey using differently paced clocks, the photon appears delayed. If you trust only that distant perspective, you might think gravity truly slowed the light. But that interpretation is incomplete. The truth rests in the subtle distinction between how light moves and how we observe that motion. Light always takes the path that seems straightest in curved spacetime. To us, that path may look bent and stretched, and so we measure more distance than expected. And if gravity has altered the flow of time near that massive object, we measure more duration than expected. The speed seems reduced because the geometry has changed, but the local speed of the photon is perfect, untouched. This idea can feel slippery. We like notes on a musical page that stay fixed. We want map lines that do not shift beneath our feet. Yet the universe does not promise consistency across the landscape. It only promises consistency within your immediate surroundings. Local laws of physics remain identical everywhere, but local is not universal. That is the quiet loophole that keeps Einstein truths alive. Consider a thought experiment. You hover near the surface of a giant bright star. A friend watches you from far away where gravity is weaker. You both carry precision clocks, powered by atoms counting tiny vibrations. To your friend, your clock ticks more slowly. The star's immense mass pulls on space-time, altering the flow of time itself. You feel nothing. You breathe normally. But your seconds stretch. If you send a beam of light that loops around the star and returns to you, you measure the same familiar speed. If your friend measures the same journey from afar, they find a longer duration. The photon has not changed. The relationship between your clocks has changed. Reality becomes stranger still when we remember that space also warps. Distances near mass expand in a way our senses cannot detect. A meter measured close to a massive object is not the same as a meter far away. So even if a distant observer insists on applying their own ruler to the path the light took, they misjudge the length. The universe does not offer a single shared measuring stick. It offers an intricate web of local frames. To compare them is to compare different languages that only translate imperfectly. This is the great revelation. Light is constant because space-time is allowed to shift. The speed of light shapes the geometry. The geometry shapes our perception. Gravity is not slowing the photon. Gravity is redefining what speed means in a curved environment. When this insight was first tested by bouncing signals off planets and stars, the results were almost mystical. The round-trip delays whispered that space near the sun was stretched. Physicists finally understood that the delay was not a failure of light. It was a triumph of relativity. The photons moved exactly as they should. The universe kept its promise. As we look deeper into the cosmos, this constancy becomes a guiding light. When we see light bent and delayed by clusters of galaxies, we do not imagine photons slowed by some cosmic fluid. We see the invisible architecture of spacetime revealed by its most faithful traveler. Photons glide where geometry leads them. They show us what gravity truly is. The constancy of light does not trap us. It frees us to explore without fear that logic will crumble. Even in the most extreme places, even near black holes where time itself nearly stops, the local truth holds. Light does not falter. We are the ones who falter when we forget that our perspective is only one among many. So as we complete this first chapter, we stand at the edge of a vast transformation in thinking. We must abandon the simple picture of gravity pulling on objects. We must embrace the deeper idea that mass and energy reshape the very stage where motion unfolds. The speed of light remains unbroken, declaring how reality must bend. Now that we accept this rule, a new question rises. If gravity is not a force, what is it? How does the universe choreograph the dance of stars and planets? And what does that choreography mean for the beams of light threading through the darkness? The answers await in the geometry of spacetime itself. There is a quiet moment in the story of physics when a simple question begins to dissolve everything we thought we understood. We have lived for centuries with the idea that gravity is a pull, that planets are yanked towards stars, that the apple falls because Earth drags it downward. This idea feels natural because we feel its strength every moment of our lives. Yet nature does not care about what feels natural. Nature follows a deeper logic, waiting to be uncovered. Einstein looked at the problem with fresh eyes. He noticed something most people ignored. When you are in free fall, when gravity is the strongest influence in your life, you do not feel anything. A person falling in an elevator toward the ground does not feel heavy. They feel weightless. The sensation of weight that we call gravity vanishes in that plunge. This is not a trick. This is a clue. If gravity were truly a force pulling downward, why would it disappear exactly when you seem most under its control? Einstein realized that the apple falling from a tree and the astronaut floating in orbit share the same truth. They are both following natural paths through space-time. Those paths seem curved from our point of view, but only because space-time itself is curved. The apple is not pulled downward. The Earth does not tug at it. The apple is simply traveling straight in a landscape that bends around mass. To picture this, imagine a stretched sheet of fabric. Place a heavy sphere at the center, and the sheet sinks beneath its weight. Roll a smaller ball near the sphere, and the path curves inward. You would say the large sphere is pulling, but it is not. The curved surface guides the smaller ball. It travels straight according to the geometry, though from above it seems to spiral. Now remove the fabric and expand that idea into three-dimensional space, then add the dimension of time. The picture becomes impossible to draw, but remains true. Mass tells space-time how to curve. Space-time tells objects how to move. This is the poetry carved into the mathematics of general relativity. Your footsteps, your heartbeat, the orbit of the moon, the dance of galaxies, all follow the curved geometry. Every object coasts along the shape defined by mass and energy. If you stand on the ground, the reason you feel weight is not that Earth pulls you down, but that the ground stops you from falling freely along the curved path that space-time intended. The floor pushes upward, blocking your natural motion, and that push is what you feel as weight. There is something profound hiding in that reversal. Gravity is not a force. It is resistance to freedom. This understanding is not philosophy. It is tested reality. The time on planets and stars ticks differently because the geometry near mass flows differently. Atomic clocks have proven it. If you lift a clock higher away from Earth's center, it runs slightly faster. If you bury a clock deep underground, buried closer to the mass, it runs more slowly. Gravity does not merely influence objects, it changes the behavior of time itself. Then consider distance. Near a massive object, the meaning of length is altered. The straight line between 2 points is not the same straight line it would be in a region with less gravity. Even if our eyes insist the space is smooth and flat, the underlying geometry is quietly bent. These changes in time and space are not illusions created by perception. They affect every electron in every atom. They alter the steps light takes as it travels. They guide planets without exerting force. Once you grasp this, the universe looks different. Stars do not hold planets hostage. Planets follow the natural grooves carved in space-time around stars. Everything moves as if sliding along invisible contours. We stand in a valley carved by Earth's own mass. Light skims along curved ridges in the fabric of the cosmos. If something looks like falling, it is actually gliding. At first glance, this explanation seems more complicated than the simple idea of a gravitational pull. But the old view leaves too many puzzles. How does gravity travel? How does the pull adjust instantly across vast distance? Why does everything fall with the same acceleration regardless of mass? Classical thinking cannot answer these questions without contradictions. Geometry answers them all through a single elegant principle: space-time curves, and everything follows the curve. This insight connects directly to the speed of light. Because light is the ultimate traveler that always moves at the same speed locally, it becomes the perfect explorer of geometry. If space-time curves, light will reveal that curve in its path. When starlight bends around a galaxy cluster far away, the photons are not being pulled sideways by some invisible hand. They are following the straightest possible route, but straight itself has been twisted by mass. Einstein's prediction of starlight bending was tested during a solar eclipse in the early 20th century. The apparent positions of stars near the edge of our sun shifted ever so slightly, just as the curved geometry demanded. This confirmed that space-time is not a silent backdrop. It is the very essence of motion and connection. Nothing in our daily experience prepares us for a reality where time slows with gravity, where space stretches and folds, where the straightest journey becomes a curve with no force behind it. Yet our instruments show that this is how the universe truly behaves. The old idea that gravity is a pull held us back from understanding light's greatest secret. Light does not fight against gravity. It moves naturally through the warped design that gravity creates. Light does not slow. Light does not struggle. It obeys a geometry that we are only beginning to comprehend. We now stand ready to explore what this means for the way photons travel near stars and planets, how gravity changes the route without changing the speed, how illusions of delay and hesitation emerge only when one viewpoint is compared to another. To see more clearly, we must follow a beam of light through the curved terrain of space-time and watch how our measurements twist the result. Gravity reaches into every experience you have ever had, yet it hides its true nature behind familiarity. We think we understand it because we feel its grip from the moment we learn to stand. But what we feel is not gravity itself. What we feel is the ground refusing to let us fall. The force in your legs as you stand still is not Earth pulling you downward. It is the resistance that prevents you from traveling along the natural curve of space-time that your body yearns to follow. If the ground vanished, you would drift freely. The weight would disappear. Gravity would still be present, shaping the space around you, but you would no longer notice it. Einstein's great realization was that free fall is the closest thing to true rest. A falling object feels no push or pull. Astronauts floating inside a spacecraft feel peaceful and relaxed, even though they are encircling Earth at tremendous speed. They feel freedom because they are following the curve space-time dictates. These astronauts are not suspended above Earth. They are constantly falling toward Earth. The surface of the world keeps dodging their approach as they rush forward. Spiraling around a planet is simply falling without ever reaching the ground. This perspective changes how we interpret motion. When planets travel around stars, they are falling too. The star mass curves space-time around it, creating a valley that guides the planet path. The world you live on glides along this valley every second, so smoothly that you do not notice the motion at all. Stars circle within galaxies for the same reason. Galaxy clusters swirl around even larger structures in the cosmic web that stretches across hundreds of millions of light years. Everything is shaped by geometry. Yet there is something even stranger. Geometry is not only bent by mass, energy and pressure also sculpt its form. The movement of light, the existence of radiation, even the vacuum state of the universe influence the shape of space-time. This means reality is not static but responsive. It flexes, it curves, it expands. The familiar notion of empty space having no properties dissolves. Even emptiness has a structure that changes with time. Light reveals these subtle shifts. Picture a single photon leaving a distant star, threading its way through the cosmic darkness. As it passes near a massive object, the curvature of space-time changes both its direction and the meaning of distance. From the photon point of view, everything is fine. It continues at the same speed as always. But if a distant observer measures its journey, the path has stretched. And if time near that massive object flows differently, the timing of the journey appears longer. The observer insists the photon slowed, but the photon obeyed its rule perfectly. Speed equals distance divided by time, and both distance and time have changed. Our instruments allow us to test this truth with extraordinary precision. Radio signals sent from Earth to satellites in orbit show that time dilation must be corrected for those satellites to report accurate positions. Without accounting for the difference in gravitational time flow, global navigation would be lost. A spacecraft orbiting a planet must adjust for geometry to ensure communication remains aligned. We are not only theorizing these effects, we live in a world where our tools acknowledge the warping beneath our feet. The geometry of space-time reaches into thought itself. Consider this question. If gravity is geometry, how do we describe a straight line? In the absence of mass, a straight line is the path a photon takes through empty space-time. But if space-time curves, that straight line follows the curvature. It is still the straightest possible journey locally. When we say light bends around a star, we really mean that the star has changed the meaning of straight in that region. This realization leads to a profound shift in understanding. There is no such thing as a universal straight line. Straightness depends on the shape of the world around you. If you draw a line across a curved surface, it may look bent from a distant point of view, but the line itself remains true to the surface it inhabits. That is how light behaves. It obeys the truth of its own environment. Even the familiar idea of gravitational attraction between two bodies becomes a misunderstanding when viewed through this lens. There is no invisible tether pulling the moon toward Earth. Instead, the moon glides along a path determined by the curvature of space-time around Earth. If Earth vanished, the moon would not feel an abrupt loss of force. It would continue forward in a smooth trajectory through flat space-time, never curving inward again. Gravity is not a thing that can be turned off. It is a condition created by mass and energy. Remove the mass, and the condition vanishes. The motion continues without interruption. This understanding is both elegant and unsettling. We no longer picture forces acting across the void. Instead, we imagine a universe where geometry choreographs every movement, from galaxies drifting in cosmic expansion to photons skimming past black holes. This geometry is dynamic. It shifts with every change in mass or energy. The universe is alive with curvature, yet the deepest mystery has only begun to emerge. When we accept that gravity is geometry, we must confront the fact that time is not independent from space. They are woven together into a single entity. When geometry curves, it curves both space and time. This means gravity changes not only where you go, but how you experience each moment. If you stand in a stronger gravitational field, your seconds lengthen compared to someone far away. If you climb out of that field, your seconds shorten. Time is not universal, it is personal. This truth is essential to understanding why light speed appears different to distant observers. Light never slows down locally. It moves through its immediate surroundings with unwavering precision. But when two observers exist in regions where time ticks differently, their measurements will never match. One sees delay, the other sees perfection. The contradiction is resolved by remembering that gravity changes reality itself. The universe does not ask whether we find this comfortable. It simply behaves this way. Einstein equations describe the rules of curvature. They show how mass bends spacetime, how spacetime guides motion, and how light reveals the path. These equations have been tested in every direction we can explore. They have passed each challenge. General relativity remains our most accurate description of gravity ever discovered. Now, we are prepared to follow light into the heart of this geometric truth. The next part of our journey will show exactly how the illusion of light slowing down appears when paths stretch and clocks disagree. We will see that every delay is a clue, every bending of a beam a signature, every shift in timing a message from space-time itself. Light becomes our guide not by choice but by design. It follows the deepest script of the universe and never deviates. If space-time bends, light bends. If time slows, the timing of a photon journey stretches. Yet light itself never changes its own pace. It is the geometry that does the shifting. Let us place ourselves near a massive star, not too close to be torn apart by its blistering heat, but close enough to feel the very shape of space-time tighten around us. A beam of light leaves a spacecraft hovering near the star and travels outward toward a distant observer far away in calmer space. The distant observer waits, watching for the signal return. The seconds tick by, and the timing seems wrong. The light arrives late. The path has taken longer than expected. At first glance, this looks like slowdown, a delay, a weakening of light speed. That conclusion is natural, but natural does not mean correct. The delay we measure is not in the photon itself. It is a story told by warped reality. Near the star, time moves differently. Clocks tick more slowly in deeper gravity. A second in that region contains more duration than a second far away. Even if both observers believe they are counting honestly, their measurements do not agree. The star does more than stretch time. It reshapes distance as well. The shortest path in a curved environment is not the one our flat thinking expects. Light follows the straightest possible route through space-time, but straight itself curves inward when mass is nearby. Even the meaning of length is altered. A meter close to a strong gravitational field is not the same as a meter in a gentle one. The space between markers expands, though our eyes are blind to the change. If our distant observer insists on calculating speed using her own ruler and her own clock, she concludes that the photon moved more slowly. But that calculation hides the fact that she is comparing the motion of light in one gravitational environment with measurements created in another. It is like comparing footsteps in sand with footsteps on hard ground, while pretending the surfaces are the same. This misunderstanding once caused great debate. The radar signals bouncing near our sun returned late. Some believed that gravity must slow the photon, but Einstein vision predicted the truth. The delay is caused by curvature, not hesitation. Light remains the guardian of cosmic speed, unwavering as ever. Space near the sun is stretched and time flows more slowly. The path is longer than it looks. The seconds are deeper than they feel, so the journey takes longer. But the value of speed measured locally never changes. This realization carries us toward the heart of general relativity. Gravity is geometry. It changes the structure of the stopwatch and the ruler. If you try to use tools designed for flat space-time in a curved one, the numbers betray you. Calling this a slowdown of light is like blaming a river for taking longer when the canyon walls twist the path. The river keeps its pace. The world around it bends the flow. Once scientists accepted that gravity alters the measurement of time, they began testing it everywhere. Atomic clocks carried high above Earth tick slightly faster than those on the ground. Clocks flown in aircraft and compared later show the effect perfectly. Even climbing a tall building gives time a tiny advantage over those below. The entire surface of our world is a gentle slope in the realm of space-time. We all age differently depending on altitude without ever noticing. Space is not uniform, time is not universal, and light reveals this with exquisite clarity. The constancy of light speed demands that the universe pay the price by letting geometry give way. If mass could not warp space-time, the rule would break. But the rule is sacred, so the universe bends. When light curves around a galaxy cluster millions of light years away, astronomers see multiple images of the same background galaxy. The photons are arriving through different routes, stretched across the geometry. It looks as if the cluster is acting like a lens. But there is no glass in this lens, only gravity reshaping the canvas of the cosmos. These delays and distortions are not accidents. They are signatures of the true nature of gravity. They tell us that we are not living in a picture drawn on a flat screen. We are navigating a vast and flexible architecture. Light is the probe that maps its hidden structure. Every time light bends, we learn the shape of the curve. Every time a signal arrives late, we witness the slowing of time itself. Yet a strange subtlety remains. When we describe space-time as curved, we often think only of large effects like stars or galaxies bending rays of light. But curvature lives everywhere mass does. Even your body bends space-time around you. The effect is unimaginably small but real. When you move your hand through the air, space-time shifts ever so slightly to accommodate it. This truth feels impossible because our senses evolved to ignore microscopic distortions. But physics does not ignore them. It measures them with patience. The idea that gravity is geometry can leave us unsteady. We are used to forces pushing and pulling. Here we face something gentler but far stranger. Motion itself is a whisper from the structure of reality. A planet does not need to know where the sun is to orbit it. The planet simply follows the shape of space-time. A falling apple is not summoned downward. It is released into its natural path. What we call falling is simply traveling straight when straight leads inward. Light teaches us this lesson more clearly than any other traveler. It never slows. It never grows old. It does not care how warped the world becomes. It moves as if space-time is a road perfectly carved for it. And if the road winds or stretches, the changes belong to the road and not to the traveler. Gravity does not hold light back. It lays out a different journey. And to understand what we observe, we must untangle perception from reality. We must learn to trust the photon, not the ruler. We must listen to the message in the delay. When light returns late, the universe is not hesitating. It is speaking. As we leave this chapter, we carry a revelation that will guide every step ahead. Gravity is not a force pulling downward. Gravity is the bending of the universe itself. Time and space are not fixed backdrops, but living participants in motion. And in this shifting landscape, light remains the unbroken law. The next chapter will show how this reshaping of reality creates the illusion that light slows down in gravity, even though the photon never loses its stride. The delay we measure is a story told by warped time and curved distance. Now that we understand what bends, we can see what illusion awaits. Light does not know hesitation. From the moment a photon is born in the heart of a star or in the spark of a switch on Earth, it races forward with unwavering commitment. Yet when that photon passes near a massive object, something peculiar appears in our measurements. We find that the journey has taken longer than expected. Our clocks on distant spacecraft and stations record a delay. We call this the Shapiro delay. named after the scientist who first predicted and later confirmed it with great care. At first glance, the conclusion seems irresistible. The light must have slowed. How else could it take so long to return? But the universe delights in tricking our expectations. This is not the photon fault. This is the universe revealing that our ideas of distance and time cannot be trusted in the presence of gravity. Imagine a beam of light leaving Earth and traveling toward the region near our Sun. It skims close to the bright surface and then returns to us. The calculation for a round trip through empty space would give a certain expected time, but gravity refuses to allow empty space near a star. The geometry there is warped. Space stretches, time slows. The path is longer, the seconds are deeper, so the journey takes longer. The distant observer sees delay. The observer near the star sees perfection. Both are correct within their own frame, but only one understands the truth of curved spacetime. To see this more clearly, picture two scientists performing the same experiment, each carrying clocks so precise that they count the tiny vibrations of atoms. One stands far from any intense gravitational field. The other hovers close to a massive star. When the beam of light travels past the star, the nearby scientist measures the speed using the local ticking of the local clock. The result is the same constant speed of light as always, because the photons are judged by the standards of their immediate surroundings. Meanwhile, the distant scientist waits for the signal to return. The clock far away ticks faster. The space far away is less curved. When she divides the distance, she believes the photon traveled by the duration she counted. The number is smaller than expected. She concludes that the photon must have slowed. Here the misunderstanding is born. The difference is not in the light, it is in the comparison. Two clocks in two different regions do not keep the same rhythm. Clocks closer to mass experience time more slowly. Distance near mass stretches in a way no ruler can capture. The speed appears slower only because one observer insists on using tools that belong to a different environment. This is the illusion of light slowing down. When radio signals were bounced off planets to test this effect, the results were undeniable. The pulse returned later than Newton would predict. It matched Einstein equations perfectly. Delay is a natural consequence of geometry. Yet still some wondered whether the photon was directly influenced by gravity in the same way that a thrown stone is influenced. But this thought fails a crucial test. Light has no mass. Gravity does not pull on photons the way classical thinking suggests. Instead, gravity bends space-time, and light simply follows the bend. This behavior becomes even more striking when the path curves enough to create new images of faraway objects. When a cluster of galaxies lies between us and a more distant source of light, we sometimes see multiple images of the same object. The photons have traveled different curved routes through space-time, arriving at slightly different times. The images are shifted across the sky like reflections in a hall of mirrors. This phenomenon is called gravitational lensing. It is not a failure of light, but rather a revelation of the hidden structure of the universe. Delay becomes distance, and distortion becomes direction. Light maps the curves for us. Every extra moment in the journey is a clue. We can measure these tiny hesitations and reconstruct the shape of space-time itself. The illusion deepens when we consider how the human mind interprets speed. We imagine that speed is simply how far something travels in a certain number of seconds. But this formula assumes that distance and time are universal quantities. They are not. When space-time curves, distance and time lose their simple meanings. They become flexible. They depend on the observer position. They depend on the strength of the surrounding gravity. They depend on the geometry that holds everything. This is why one observer can swear that light slowed, while another finds the familiar constant. The universe allows both experiences because each one is using clocks and rulers shaped by their environment. The deeper truth is that light retains its divine consistency. It never changes. We are the ones comparing worlds that cannot be compared. Once this realization takes hold, the illusion begins to dissolve. When we see delays and shifts, we must not ask what slowed the photon. We must ask how gravity has reshaped the journey. We must ask what the curvature of space-time has done to the map we thought was flat. A photon near a massive object does not behave as a car does on a road. It does not push harder to overcome a hill. It does not feel slower on a slope. It glides effortlessly at the same speed through the only path space-time allows. If the path stretches and twists, the difference belongs to the path, not the traveler. Even the name Shapiro delay fails to capture the elegance of the effect. It is a window into a universe where speed remains perfect, but the tools of measurement are bent. It tells us that gravity can play tricks on perception without touching the fundamental rules. It reminds us that our thinking must evolve beyond our first impressions. This chapter reveals the illusion clearly. Light appears to slow in gravity. It does not. Light follows the shape of space-time. The shape is curved. The path is longer. Time is altered. The photon remains pure. As we continue deeper into the nature of gravity, we will watch light bend more dramatically. We will see how galaxies can be magnified and multiplied. We will explore how speed remains constant while reality dances around it. And we will finally understand that what changes in gravity is not light, but the very stage upon which time and space perform their endless performance. Light moves with unwavering certainty, yet what we see can mislead us. A photon leaving a spacecraft appears to travel slower when it glides near a massive star. We stare at our measurement and believe the universe has allowed its greatest constant to waver. But this belief comes from trusting our clocks and rulers in a world where neither can be trusted. Gravity does not push on the photon, it bends the map beneath it. To grasp this clearly, imagine the simplest path of light in flat space. A beam travels from one point to another, and the time it takes is perfectly predicted. But now, place a massive star between the starting point and the destination. Space near that star is distorted. The shortest path a photon can take is no longer the straight line we expect. It curves inward, slipping closer to the star. The distance grows even if it does not look that way to us. And because gravity slows the flow of time near the star, the seconds stretch. The clocks used by an observer far away tick faster than the clocks near the star. One observer measures a longer trip. The other sees the same constant speed. The same event carries two truths because two different frames of space-time disagree. Both are correct inside their own reality, but only one understands that geometry has changed. If you could float beside a photon near a star, you would measure its speed using your own time. That time is shaped by gravity. You would still find the same sacred number that defines the speed of light. If your friend far away makes the same measurement using her own time, shaped by weaker gravity, she finds what appears to be a slower speed. The difference arises because both of you are counting different seconds. Einstein insisted that physics must hold true in every local frame. Every observer near the events they measure must see the laws stay consistent. That is why the photon never slows locally. But when we stretch the comparison across regions of differing gravity, our minds invent a problem that does not exist. The illusion of slowdown is created by our need to pretend that time is shared equally everywhere. Delayed signals from spacecraft, long journeys of beams reflecting off planets, these are not glitches. They are lessons. They tell us that distance is not carved in stone and time does not beat in unison. They reveal that the universe is not rigid but elastic. Now imagine a photon traveling past a massive galaxy cluster. These clusters contain thousands of galaxies bound together. The combined mass bends space dramatically. A background galaxy shining from far away sends its photons through this curved space-time. Some of those photons take one curved path, others take another. They arrive at our telescopes at slightly different times. We see the same galaxy appear in multiple places in the sky, multiplying like an illusion in a vast cosmic mirror. This is gravitational lensing. It is not trickery. It is the true structure of space made visible. Light always shows the geometry. When we misjudge the journey, we create the false belief that something slowed it. But what has changed is the meaning of straightness and the passage of time. The universe invites us to imagine something else. Suppose an explorer launches a beam of light directly toward the surface of a neutron star. Neutron stars are made of matter so dense that a single spoonful would outweigh mountains. The curvature there is powerful. The photon races freely as always, but the geometry is so deeply altered that the path becomes dramatically steep. Time crawls near the star surface. If the beam reflects off a mirror placed just above the crust and comes back, the delay experienced by a faraway observer could be enormous compared to the same round trip in calm space. Yet the photon has not slowed one moment. It has only obeyed the rule that movement is guided by curvature. And what of the famous slowing that appears near black holes? The most extreme gravitational objects in the cosmos stretch time to its breaking point. A photon falling toward a black hole horizon seems to freeze in place when viewed from the outside. It appears to lose all progress. But that is only what we see when we attempt to judge its motion using our own faster clocks far from the event horizon. The photon life near the horizon is measured in a different rhythm. The illusion becomes complete because the time near the black hole drags toward infinity. This is perhaps the most powerful demonstration of how gravity creates the illusion that light slows. The photon stays faithful to its speed, but the clocks of a distant observer race forward while the photon rides the slow heartbeat of warped space-time. From far away, the light looks hesitant, frozen even, but it is our view that is broken. Our trust in familiar thinking stands in the way of understanding. We want time to pass the same way everywhere. We want space to stretch the same distance between markers in every place. Our world taught us those expectations. But our world is only a small patch of the universe, one where the curvature is gentle and easily ignored. When we explore beyond Earth, the weaknesses in our thinking emerge. Gravity is not a force tugging downward, it is a reshaping of reality. And light, the most loyal messenger in the cosmos, reveals that reshaping in every path it takes. We call it slowing. But slowing is the wrong story. The correct story is that of a road changing length and a clock changing speed beneath a traveler who remains unchanged. This chapter strips away the illusion. It shows us that our measurements are not universal truths, but agreements made among clocks and rulers that share a similar environment. When that environment shifts, the agreements fall apart, and still, the photon rushes on. In the next part of this chapter, we will dive even deeper. We will see how light path around large objects proves that the geometry is not straight. We will discover that what looks like bending is really straightness itself, redefined by gravity. And we will learn how these distortions allow us to peek behind cosmic curtains and see things no eye could otherwise behold. Light is the master of straight lines, yet in the universe, those straight lines do not always behave the way we think they should. When we draw a line upon a flat sheet, we believe we understand straightness completely, but that confidence comes from living inside space-time that is only gently curved. When mass enters the picture, straight lines become something far stranger. They follow the deepest shape of the cosmos, not the flat shapes our eyes expect. This is why light appears to bend when it moves near a massive object. Not because the photon has changed its mind or bowed to a force, but because the universe itself has redrawn the meaning of straight. Imagine a beam of starlight traveling across the sky. From our viewpoint on Earth, we see it shift position slightly when it passes near our sun. During an eclipse over 1 century ago, astronomers finally proved this subtle shift. The stars did not move. Their light passed through curved space-time. The path was true to geometry, but geometry itself was not straight. Einstein's prediction was confirmed beneath the suddenly revealed stars at the edge of the sun's shadow. That night marked the first global victory for the idea that gravity is the bending of the stage, not the pulling of the actors. To understand this bending more deeply, imagine sliding a marble across a smooth table. It glides in the direction you set it. Now imagine placing a heavy sphere beneath the tablecloth and letting the marble roll again. It will take a curved path, not because a hand is pulling it sideways, but because the surface has changed shape. The marble always seeks the easiest route. In curved space-time, light does the same. The photon does not feel deflection, it simply follows the natural shape drawn by mass. Now scale this simple picture to a galaxy that contains trillions of stars. The mass bends the region of space-time around it so dramatically that the light of even more distant galaxies bends around this mass like a river flowing around a stone. To a telescope on Earth, this bending creates rings, arcs, and multiple mirrored images across the sky. These are called gravitational lenses. They are the universe revealing its curvature directly to our eyes. When you look at these cosmic arcs, you witness the exact effect that once made scientists believe light slowed near stars. The photon travels through a longer route because the straight path is stretched. The geometry is warped. What seems like a delay is simply extra distance. What seems like a bend is the new definition of straight. The constancy of light speed remains untouched, hidden behind illusions created by the curvature of space. Time also joins the dance. In the presence of mass, time does not pass at the same pace everywhere. The deeper you move into a gravitational well, the slower time becomes. So a photon traveling near a massive object moves through deeper time. If you watch that journey from far away, your sense of time races faster. You are measuring the same process with seconds that pass more quickly. When you divide the stretched route by your hurried seconds, the number seems smaller. You say the speed is reduced, but the photon does not change. The clocks do. This leads to a profound realization. Light has no voice. It cannot tell us directly that its speed remains perfect. We hear only the echo of its motion and trust our measurements. But measurements are created inside space-time. When space-time bends, the numbers are bent too. The illusion is perfect unless we know where to look. Every tool we invent must bow to this truth. The satellites orbiting Earth that guide travelers around our world carry clocks that tick slightly faster than those on the ground. Engineers must correct for this difference so that a location on a map does not drift from the place beneath your feet. Without accounting for the slowing and speeding of time in gravity, the entire navigation system would fail within hours. The planet rotation, the orbits of worlds, everything would seem to slip. The universe always warns us when we try to force flat thinking onto a curved reality. Light shows the error first. It arrives late. It shifts its path. It splits into multiple destinations. It refuses to match the naive predictions of a world without curvature. These surprises are not accidents. They are messages from space-time itself. The cosmos keeps telling us that our understanding must change. When we see a delayed signal, we are witnessing time being stretched. When we see bending and arcs, we are witnessing space being pulled into curves. Each observation gives us a chance to rewrite the map of gravity. What once looked like a flaw in the universe turns out to be evidence of deeper perfection. The illusion that light slows in gravity is born from comparing what should never be compared. A distant clock and a local clock do not count the same seconds. A ruler in curved space does not mark the same length as a ruler in flat space. If you trust one and not the other, the photon appears guilty of breaking the law. But the photon is the only one that remains faithful. The laws bend before the photon ever does. This is not only a scientific truth, it is a new way to think about reality. What we see is shaped by where we stand. What we measure is shaped by the gravity around us. There is no single viewpoint that holds the whole truth. The universe is a chorus of perspectives, each one correct in its own place. Light brings us these perspectives. It allows us to compare one region to another. It reveals how the heartbeats of clocks differ. It reveals how the tapestry of space stretches and folds. It reveals that gravity is the creator of illusions, yet nothing about light is ever a lie. In this chapter, we have uncovered the illusion. Light appears to slow down. Light appears to hesitate, but appearances crumble when we understand that geometry itself is shifting beneath every step the photon takes. Now that we have learned this, we are ready to see how bending space gives rise to the most stunning displays in the cosmos. Gravity can turn a single distant galaxy into beautiful arcs of light. It can magnify regions of space that would otherwise remain hidden. It can let us look farther into the past than any telescope could dream without the universe's help. In the next chapter, we will follow light as it curves through cosmic valleys and climbs over spacetime hills. We will witness the power of gravitational lensing and understand why these visions prove that straight lines do not always point where we expect. Light travels with absolute loyalty to the geometry around it. It never questions the shape of spacetime. It never resists the curvature that mass creates. When we see light bending around a massive cluster of galaxies, we might be tempted to imagine the light struggling against some great pull. But this thinking belongs to an older age. What appears as bending is actually the straightest possible motion when the world itself is curved. A photon always follows the path nature defines as straight. It is our understanding that bends when we try to fit curved spacetime into flat expectations. Imagine a galaxy cluster so large that its mass outweighs hundreds of trillions of suns. The spacetime surrounding it becomes a deep valley in the cosmic landscape. Light from a more distant galaxy travels into this valley. To us, watching from far away, the path curves inward and then outward again, like water flowing around a stone in a river. But from the photon point of view, nothing extraordinary occurs. It moves straight ahead through its own local geometry. The cluster has simply transformed the nature of straightness. When this bending is strong enough, something wondrous happens. The distant galaxy appears in more than one place at once. Multiple beams of light leave the same object, thread through different curves in spacetime, and then all converge again at our telescope. We see clones of the original light source spread across the sky. Our instincts say this violates common sense, but sense is shaped by flat terraces of Earth, not by the wild curves of the universe. Sometimes the geometry is perfectly aligned. The mass of the foreground cluster forms a circular warping of the background light. The result is a complete ring of brightness surrounding the massive center. We call this an Einstein ring, though Einstein himself only realized in theory that such a sight could exist. These rings are not rare illusions. Telescopes record them throughout the heavens, preserving the signature of curved geometry as if space were painting perfect circles for us to admire. But gravitational lensing is not only beautiful, it is revealing. Because the light has taken multiple curved paths, it arrives at slightly different times depending on how deeply each path dives into curved spacetime. Some photons explore the deepest part of the valley and emerge later. Others take quicker routes around the edges. The arrival times differ by seconds or even days for distant galaxies. This delay, far from proving any slowing of light, confirms precisely how space-time curves. It teaches us the shape of the invisible. We do not need cosmic giants to see this effect. Even our sun, though small compared to galaxies, bends the light of distant stars passing near its edge. During a solar eclipse in the early 1900s, astronomers photographed the sky near the sun and found that the positions of stars shifted exactly as relativity predicted. It was not magic. It was not coincidence. It was the Earth witnessing for the first time that space around our sun is not straight. To a photon passing near the sun, nothing unusual is happening. The beam glides at its constant local speed. But to us, the path has bent. And so, once again, two different truths exist side by side. The photon obeys its rule. Our measurements reflect our vantage point. The illusion belongs to the observer, never to the light. Picture space as a fabric that can stretch and ripple. Mass presses into this fabric, making gentle slopes around planets and steep valleys around black holes. Light flows along these shapes, not because it is pulled, but because the geometry leaves no other option. A beam of light near a massive galaxy cluster might take a path that loops wide around the cluster. Another passes closer to the core. A third might swing behind it entirely. From a distance, each of these paths looks like an intentional curve. But in the local geometry, each is a perfect straight line. This raises an astonishing thought. There is no absolute straightness in the universe. Straightness is always tied to geometry. What looks curved from a flat point of view is simply following the deeper truth of space-time. If we fully embrace this concept, every bending of light would become a message. We would stop asking why the photon curved and instead ask what the curvature tells us about the mass hidden there. This is how astronomers weigh the invisible. Many galaxies we observe are surrounded by extensive halos of matter that emit no light. We call this unseen substance dark matter. Its presence is revealed not by direct observation, but by how it bends the space around it. When light from background galaxies stretches and twists as it passes through the halo, we map those distortions. In this way, gravitational lensing becomes our most powerful tool to explore the mass that refuses to shine. Gravity tells light where to go, and light tells us where gravity is hiding. When we look at those distorted shapes, when we measure those delays, we are reading a cosmic script etched into the geometry of the universe. The script says again and again that space is curved, that straight paths are illusions born of small worlds, that our minds must stretch as far as light stretches for us. And when we ask how long light took for each detour, we rediscover the same lesson from the Shapiro delay. The photon does not slow in the valley. It crosses a landscape that has grown longer and moves through time that has grown slower. The illusion is forgiven once we remember that speed is distance divided by time, and both distance and time are altered by gravity. This entire chapter could be summarized in a single sentence. Light proves that space is not straight, but behind that simple truth lies a transformation in understanding. The universe is not flat. Gravity is not a force, and what looks like slowing, bending, and hesitation are all reflections of curved reality. As we move forward, the illusion becomes even stronger near the most extreme objects that exist. When light approaches a black hole, the bending becomes so severe that the path seems to loop entirely. Time slows almost to a stop, and from far away, the photon looks like it is losing the race against the universe. Next, we will follow light to the edge of that abyss and discover what really happens when geometry becomes so twisted that not even light can escape. Light does not complain when the universe becomes strange. It does not hesitate when space-time twists into unfamiliar shapes. It simply continues forward, following the straightest path the geometry allows. But near a massive object, especially something as dense as a black hole, the idea of straightness becomes almost unrecognizable. It is here that we see the most dramatic demonstrations that space is curved, that time is altered, and that what seems like bending is the universe revealing its true architecture. Imagine watching a distant star. Its light travels peacefully across the cosmos, unaware of anything in its way. But between you and that star sits an enormous object, perhaps a galaxy, or even a cluster of galaxies. That mass bends the fabric of space-time, reshaping the road ahead. The light wraps around the mass, splitting into multiple routes. Each route maintains the same local speed of light. Each one remains true to geometry, but when they arrive at your telescope, the star appears in several different locations at once. Time stamps from each route differ. Some photons arrive earlier, some arrive later. The cluster has become a lens made of gravity, a lens made of curvature. We look into the universe and see patterns that would be impossible in a flat world. Long arcs form around galaxy clusters like the arms of cosmic sculptures. These arcs show us the hidden mass lying within and around the cluster. Much of that mass is dark matter, invisible to any telescope except through the distortion it causes. Without this bending of light, we might never have known that most of the matter in the universe refuses to shine. Light is our detective. Light exposes the invisible. Consider another example that reveals the same truth. A supermassive black hole sits at the center of a galaxy. Its gravity is so intense that space-time plunges steeply around it. If a star lies directly behind that galaxy, light leaving the star will bend around both sides of the black hole. The two curved paths rejoin and enter our instruments, forming a brilliant ring of light, an Einstein ring marked by the curved truth of space-time. The black hole itself remains dark, but the ring is a glowing map of geometry. In all of these wonders, one thing remains constant. The speed of light never changes when measured locally. The photon continues faithfully, but the terrain is stretched. The valleys are deep. The meaning of distance has changed. The meaning of time has changed. A straight line in this region bends only in the eyes of those who refuse to let go of flat thinking. The universe invites us to imagine something that feels impossible. A perfectly straight line that curves. How can something be both? The answer lies in the difference between local truth and global perspective. Locally, the photon sees no bend at all. It sails freely along what is called a geodesic, the true straight path of curved space-time. From far away, we look at that path using flat imaginations and call it curved. Both experiences are valid, but only one understands the geometry that shapes motion. When we observe these effects, we are not witnessing the failure of light. We are witnessing the sophistication of the universe. Every time a photon bends around a cluster or arrives late from behind a star, it teaches us the same lesson. We cannot trust our instinct that space is flat and time is universal. Our everyday senses lie to us because they evolved on a small world with gentle curves. We live immersed in curvature without noticing it. Even the space around you right now is bent by the earth beneath your feet. You do not see the bending. You do not feel the warping of time flowing a little slower here than one floor above. But your instruments can detect it. Your body ages at a measurable rate that depends on how deeply you sit in Earth gravitational well. Your breath, your heartbeat. Every moment is shaped by geometry. Now extend that idea to places where gravity is far stronger, where stars collapse so tightly that light itself is reluctant to climb out. Just before that reluctant border, space-time curves so steeply that light appears to orbit in circles. A photon could skim around such a collapsed star again and again if its path were perfect. From afar, that motion looks like the light has slowed, as if the photon is stuck in doubt, unsure of its direction. But this hesitation is not hesitation. It is time flowing differently. It is distance stretching beyond comfort. It is the photon obeying geometry that has been pulled nearly to the breaking point. Even near the sun, far less extreme than a collapsed star, the bending is enough to reveal the truth. When radio waves skim near our sun surface on their way to a distant spacecraft, their round trip takes longer. Our clocks record delay. That delay confirms that time near the sun is thicker, more densely packed. The photon takes a longer path than our flat maps predict. What our minds call slowing is the universe showing its curve. This bending of paths does not weaken the commitment of light. It strengthens our understanding of the flexibility of reality. Light never fights gravity. It embodies gravity. It moves along the script that mass has written into space and time. We once thought light moved in straight lines, and that space was a blank stage. But this chapter has shown that the stage is alive and active. The straight lines are participants in the dance. Photons glide through a world sculpted by every star, every planet, every hidden form of matter, and each deflection, each arc, each ring is a revelation that gravity is not a force, but a shape. As we approach the most extreme forms of curvature, light begins to reveal even more dramatic truths. Near a black hole, the bending becomes so severe that the photon path may spiral, stall, and seem frozen to distant eyes. It is in such places that our final illusions about light and gravity will be torn away. Before we travel to the edge of darkness, there is one more idea to uncover in this chapter. If space can stretch and twist, what does that mean for the energy that light carries? What happens to the waves of light as they climb out of a gravitational valley? How does frequency change when time itself shifts? The answers lie in the hills and valleys of spacetime, where light does not slow, but its color can change. To finish this chapter fully, we must explore the relationship between motion, energy, and the stretching of time. Light is more than motion. It is energy carried across the universe in waves that never slow down. Yet those waves stretch and compress as they travel through curved spacetime. This stretching is one more illusion created by gravity. To understand it, we must see how time shapes the rhythm of light. A photon heartbeat is its frequency. Each beat marks a crest in its electromagnetic wave. When time flows differently, that heartbeat changes its pace. Imagine standing near the surface of a massive star. Here, time moves more slowly compared to a distant region where gravity is weaker. Now picture a photon rising away from the star, climbing out of the gravitational valley. Near the star, each wave crest emerges slowly in the deeper flow of time. But as the photon rises toward regions where time flows faster, those wave crests begin to arrive farther apart from the perspective of a distant observer. The photon frequency appears lower. Its color shifts toward the red end of the spectrum. We call this gravitational redshift. It is not that the photon loses speed. It cannot. Instead, the rhythm of its waves stretches because the clocks measuring them speed up. Turn the situation around. Let a photon fall toward a massive object. It is now entering slower time. Each crest of the wave that once seemed leisurely and widely spaced now appears packed together more tightly by the distant observer. The frequency increases. The color shifts toward blue. This is gravitational blueshift. It too is an illusion born from time that refuses to flow evenly in all places. These changes in frequency are clues. They allow physicists to test general relativity with precision. The amount of redshift or blueshift tells us exactly how time differs between locations. Atomic clocks reveal the effect even on Earth where gravity is gentle. Light emitted near the ground has a slightly lower frequency compared to the same type of light emitted from higher in a building. The difference is tiny but real and measurable. Time, subtle yet powerful, reveals itself through the changing song of photons. All these demonstrations lead us again to the same core truth. Light never slows down. It always moves with perfect fidelity to the rules that govern the universe. When we observe something that seems like hesitation or fatigue in the photon journey, we are only witnessing the warping of time and distance. A redshift is not lost energy. It is the same energy expressed in a different rhythm because the measure of a second is different. Near massive objects, not only does the flow of time change, but the very structure of space alters the meaning of motion. Light follows the shape of space-time, and that shape is written by mass and energy. When we say a photon appears slower or delayed, we are comparing clocks that tick out of sync with each other. When we say a photon has bent, we are describing a straight path in a curved environment. When we say light loses energy climbing away from gravity, we mean that time itself stretches the intervals between the beats of its wave. Perhaps the most dramatic example of these illusions occurs in the region around a black hole. The event horizon is the boundary beyond which not even light can escape. Time there moves so slowly relative to the outside universe that a photon falling toward the horizon appears to freeze in place. To a distant observer, it never quite crosses the threshold. The wave crests stretch further and further apart, becoming redder and redder until they fade into darkness. Yet the photon does not feel any change in its own speed. It crosses the horizon normally from its own perspective. The illusion belongs entirely to the distant observer, whose clocks race ahead, while time near the horizon slows toward a halt. This confrontation with a black hole reveals the deepest lesson we have learned so far. Our perception of light is shaped by our perspective. We trust our clocks because they guide every moment of our lives. But clocks are vulnerable to gravity. They stretch and compress the measure of time. We trust our rulers, yet rulers lengthen in regions of curved space. Every measurement we take is influenced by the geometry around us. The photon obeys one perfect speed, yet we judge it with flawed tools. Light never slows. We do. We lose sight of the path when the geometry shifts. We misinterpret delayed arrivals as weakened motion. We mistake longer routes for slower travel. Our logic stumbles because our senses cling to the belief that time is universal and space is flat. But now we know better. The photon speed remains constant, untouchable by gravity. The only things that change are the depth of time and the shape of space. Gravity gives rise to illusions that fade once we learn to see the universe through the laws of relativity. We have followed light through the distorted valleys of space-time. We have watched it bend and stretch without ever truly changing speed. We have learned to separate appearance from truth, and now we must journey to the one place where illusions become overwhelming and the nature of reality itself appears to break. A black hole does not merely bend space-time. It reshapes the rules almost beyond recognition. Time nears stillness at its edge. Distance becomes tangled. The horizon is a doorway that light cannot pass through and return, at least not in any way that preserves our understanding. When we see a photon near a black hole, we are seeing the ultimate test of the idea that light never slows. In the next chapter, we will stand at the brink of the most extreme gravitational arena in the universe. We will gaze into the place where time grinds nearly to a halt and learn what it means for a photon to move constant and true through a world that refuses to allow it escape. Light carries a heartbeat. It pulses with a rhythm that defines its color, its energy, and the story it tells across the universe. Each crest of its wave is a moment in time, a tiny drumbeat marking the passage of reality itself. But time is not steady. Gravity reshapes time just as it reshapes space. And when time stretches or contracts, the heartbeat of light changes. The photon does not slow, the photon does not weaken. The universe simply counts its moments differently. Imagine standing near the surface of a massive star. The air rumbles with heat and gravity presses against every atom. In this environment, time itself moves more slowly than in the emptier regions, far from the star power. Here, a photon is born in the violent heart of fusion and begins its climb upward. Each crest of its wave emerges with the steady rhythm of local time. Yet as the photon escapes into regions where time flows faster, the distant observer sees a change. The beat seems slower, the waves stretch apart, the frequency lowers, the color shifts toward red. This is gravitational redshift. It is not a loss of speed. It is a change in how the beats of time are measured as they cross from one region of space-time to another. Now reverse the journey. Let a photon fall inward toward a massive object. It enters deeper gravity where time slows. Each wave crest seems packed closer together to the distant observer. The color shifts blue. This is gravitational blueshift. It is a sign that time is tightening around the photon heartbeat. The rhythm seems faster because the observer measures those wave crests using a different clock, one that is racing compared to the slower time below. These shifts do not violate any rule. They are not dangers or flaws. They are the language of gravity. They tell us how time changes as space curves. Light remains constant in its speed locally, but its music changes key as it crosses the shifting tempo of space-time. Across the entire universe, light constantly climbs or falls through regions where gravity is stronger or weaker. Every beam of starlight that reaches us has been shaped by these gravitational tides. Even the light from our own sun stretches slightly as it escapes the gravitational well beneath it. If we could listen to the sunlight as a song, the notes would shift gently upward in pitch if we descended closer to its fiery surface, and gently downward if we rose away from it. We rely on these shifts for some of the most subtle measurements in astronomy. When scientists place atomic clocks at different altitudes on Earth, they detect small but real differences in the frequency of photons emitted between levels. Travelers in airplanes age slightly faster because the gravity above the ground is weaker. Satellites orbiting Earth must constantly adjust their clocks to account for the difference in gravitational time flow, or navigation would drift and become useless in a matter of hours. This is not speculation. This is the universe acting on modern life. Relativity guides every journey on our planet. Now imagine the most extreme case, the approach to a black hole. The gravitational pull there is not a force dragging objects inward. It is space-time itself curving sharply and pulling time into deep wells. A photon falling toward the edge of a black hole seems to speed inward, like a diver approaching a waterfall gorge. Its waves, to a distant observer, appear packed so tight that the energy rises, shifting toward blue. But once the photon tries to escape from that steep curvature, its heartbeat stretches. The wave crests drift farther apart. The light reddens. For the distant observer, the reds become deeper and deeper as the photon climbs the endless slope of warp time. Eventually, the crests spread infinitely wide. The photon fades into darkness. It is still there. It is still moving with constant local speed. But distant clocks have raced so far ahead that the photon signal is lost to view forever. This fading at the edge of a black hole is not the photon surrendering. It is the world near the horizon, living in time that almost stops compared to our own. To us, the light seems too slow to escape. The photon appears trapped, frozen only a step from freedom. Yet in its own immediate surroundings, nothing unusual happens. The photon passes through the horizon naturally, continuing its journey deeper into the collapse of space-time. Only the observers who remain far away believe that the photon never arrives. They trust their own clocks too much. They forget that gravity has changed the rhythm of time. Gravitational redshift and blueshift reveal a danger in our thinking. We imagine that energy is something absolute, something that can be measured independently of the observer. But the photon energy depends on how quickly an observer counts its wave crests. Count faster, the energy seems greater. Count slower, the energy seems less. The photon is the same. The clocks are not. This understanding becomes vital when we study the universe expansion. Distant galaxies rush away from us as space stretches between stars. Light traveling through that expanding space also stretches. Its wavelength grows longer and redder over billions of years. That cosmic redshift is not a slowing of the photon, but a stretching of the road beneath it. The universe is expanding, and the light simply keeps pace with a path that becomes longer, while the speed remains sacred. Whenever light shifts color, the universe is telling us something deep about time and motion. A redshift whispers that the photon has climbed from a slower region of time to a faster one, or that the very fabric of the cosmos has stretched under its feet. A blueshift announces that the photon has fallen deeper into gravity well, or that an observer has rushed toward the signal. In every case, we learn that speed is not the culprit. Speed remains perfect. Reality around the photon is what has changed. The rhythm of light reveals the truth, that space-time is not uniform. It flows and curves. It speeds up and slows down. Gravity and motion reshape time itself. And the photon, the universe's most faithful traveler, adapts only by presenting us the story of that reshaping in its color and its delay. Light always moves at the speed of light. Locally, that rule is absolute. But the tempo of time is not absolute. And when time changes, the heartbeat of the photon changes in our eyes. Light never loses its pace. We lose our agreement on what a second means. As we move forward, we will take this understanding to the brink of the most extreme places in existence. We will follow photons to the edge of black holes where time nears stillness and discover how the very idea of motion unravels. The illusion that light slows there is the strongest illusion of all. Yet that illusion reveals the astonishing power gravity holds over the shape of reality and over the story light tells as it moves. This chapter has shown that when light climbs or falls through curved space-time, it does not slow or speed up. It remains constant. It only changes its tune. Now we turn toward the lesson that awaits at the ultimate frontier, where time nearly stops, where straight paths turn inward and never return, where the universe most fiercely defends that single cosmic law: light never slows, even when we fall into the depths of darkness. The speed of light is a promise written into the structure of existence. It does not bend. It does not falter. It does not negotiate with gravity or yield to the tides of expanding space. Yet everything around it can twist and stretch. Time flows differently depending on where you stand. Space changes shape depending on what lies nearby. When the environment transforms, our measurements transform too. The photon stays faithful. We mistake the world for slowing the light when the world has changed, and the light has not. To say speed is distance divided by time sounds innocent and complete. But that definition hides a complexity that lives deep in relativity. Distance and time are not absolute quantities. They are agreements between observers, shaped by motion and mass. In the presence of gravity, a clock does not tick with the same rhythm everywhere. A ruler does not measure the same length from one region to another. If speed is distance divided by time, and both distance and time are shifting beneath the photon, then our calculation of speed will shift too. But the photon itself never deviates from its sacred command. Imagine two observers watching the same beam of light. One stands near a massive object, deep in the curve of gravity. The other floats far away, where space-time is flatter. The first observer watches the beam move with perfect consistency. The second measures its progress using faster time and flatter space. When she divides the stretched route by her racing seconds, the number she obtains is smaller. She believes the light has slowed, but the two of them are counting different seconds and marking different distances. Their disagreement is not about what light has done. It is about how space-time has changed beneath it. Relativity tells us that all observers must agree on the laws of physics when they measure things locally. If you carry your own clock and ruler into your own patch of space-time, the speed of light will always be the same. This is the iron law, the constant, the great anchor of causality. But when you compare measurements across different gravitational environments, the numbers diverge. You cannot use flat thinking to understand curved reality. The universe does not allow it. To see this clearly, picture space-time as a living terrain. In regions where mass gathers, the ground slopes inward. In emptier regions, the ground is flatter. Light moves across this terrain the way a traveler moves across hills and plains. Locally, the traveler steps at the same pace. But if one observer watches from a distant plateau and tries to measure that pace without accounting for the hills, it will seem slower. The terrain changed, the stride did not. We see this effect in every corner of physics where gravity plays a role. Signals sent to satellites in orbit return with tiny differences that must be corrected to preserve navigation systems. Experiments in laboratories find that light traveling near heavy lead masses takes slightly longer than expected. Radio emissions, skimming past the sun, return to Earth with delays that match the predictions of warped space-time. The photon honors the constant speed in each immediate region, and the universe honors the constancy by reshaping itself to preserve the rule everywhere. This interplay becomes even more startling when we study cosmic expansion. The universe grows larger with every moment. Galaxies drift apart as space stretches in all directions. Light traveling through that stretching space does not slow down. but the path grows longer as the photon travels. Its wavelength stretches with the expansion, becoming redder over time. Its energy appears reduced not because it has lost speed, but because the ruler used to measure distance has lengthened during the journey. The photon remains loyal to its speed, even as reality reshapes the meaning of motion. The constant speed of light demands something profound. It demands that space-time be dynamic and flexible. It forces the laws of geometry to adapt rather than allow the photon to change. This is why time slows near mass. This is why space curves into valleys and saddles. This is why clocks disagree. The photon is the standard that the universe protects at any cost. We often ask what slows down when gravity is strong. The answer is astonishing and humbling. It is not the photon, it is us. Our clocks slow, our rulers stretch, our perception bends. We are creatures built for slow speeds and gentle gravity, living in a universe where extremes await just outside our familiar horizon. When we send our minds into the depths of relativity, we must let go of assumptions shaped by life on a small planet. Light is not merely fast, it is the definition of fast. It sets the ultimate limit on how events connect. If something outran light, then effects could precede causes. The universe would lose its logical order. Time would collapse into confusion. The constant speed of light protects the arrow of time. It ensures that the story of the universe unfolds in a consistent direction. When gravity makes light appear slow, it is revealing just how fragile our concept of time is. It shows us that the rules we take for granted are not the rules the cosmos follows. Time is flexible. Space is flexible. Light is not. As we move into the most extreme environments the universe offers, this truth becomes unavoidable. At the edge of a black hole, time stretches so dramatically that a photon appears frozen. The distant observer believes that light has been halted. But this is only the last and strongest illusion. What truly slows to a halt is time itself as it struggles against gravity that has reshaped reality into something almost unrecognizable. Light never slows. Gravity slows our experience of it. Time becomes distorted and space becomes stretched until our measurements lose meaning. The photon continues at its steady pace through twisting geometry, unaffected by the illusions it creates. This constant speed is the anchor in the shifting sea of space-time. It is the promise the universe keeps, even in the darkest places. And in the chapters ahead, we will dive directly into those places. We will follow light to the edge of a black hole. We will watch time approach stillness. We will confront the very limit where geometry becomes so extreme that even constant speed cannot return a photon to the outside world. And through it all, one truth will stand. The universe bends, time slows, perception fails, light does not. There are places in the universe where reality bends so deeply that our ordinary understanding falls apart. A black hole is not simply a massive object. It is a region where gravity has carved space-time into a steep and endless descent. At its heart lies a boundary unlike any other in nature. The event horizon is the line beyond which even light cannot return. Not because it slows, not because some force grips it like a snare, but because the very structure of space-time turns every path inward. When the geometry points only deeper, motion cannot escape that direction. To approach a black hole is to witness gravity not as a familiar gentle pull, but as pure curvature made visible. Picture yourself falling toward the event horizon. You are calm. You feel no great force. The spaceship around you drifts as if someone simply let go. There is a surprising silence in this fall. Nothing pulls you downward. You are simply following the curve that space-time dictates. This is the essence of general relativity. Free fall is freedom. Gravity is geometry. From your own point of view, nothing strange happens as you cross the horizon. You carry your own clock. Time flows normally for you. If you shine a flashlight in front of your eyes, The beam moves away with its same constant local speed. You are not slowed, light is not slowed. Everything continues as it always has. But a distant observer watching your descent will see something entirely different. To that observer, you never quite reach the horizon. Every signal you send takes longer to arrive. Each flash of light from your vessel appears increasingly stretched and red as time flows differently near the black hole. The wave crests of your photons drift farther apart. You seem frozen in place, hovering forever at the edge. Your image fades slowly, swallowed not by force, but by time that refuses to move forward. This is the greatest illusion gravity can create. The black hole appears to stop light in its tracks, but the stopping belongs entirely to the distant observer whose clock rushes ahead, while the clock near the horizon slows almost to a halt. From your own perspective, you fall freely inward. From theirs, you are captured in slow motion, forever delayed, locked at the very border between return and no return. One truth for the falling traveler, another truth for the distant witness. Both truths shaped by the same geometry. Why does this happen? At the event horizon, space-time curves so steeply that every possible path a photon can take leads deeper into the void. Even a beam of light fired outward from that boundary travels inward when viewed from the larger cosmic map. The photon is still moving locally at its perfect speed, but the geometry itself has changed its destination. There is no path that leads away once the horizon is crossed. Light is not defeated. The universe has changed the directions. A distant observer uses time to judge speed, but time near the black hole is drastically slower. If the distant observer uses her faster clock to measure the progress of a photon guided by slow time, the calculation denies the constant speed. She sees delay, she sees hesitation, she sees a photon that appears to lose strength and stop. The event horizon becomes a wall built not from obstruction, but from disagreement between clocks. In this disagreement, we learn something profound. Time is not a universal river. It does not flow equally in all places. In the deep well of a black hole gravity, time nearly freezes. A photon leaving the edge does not slow, but its heartbeat stretches until it becomes too faint to detect. What vanishes is our ability to witness it. This effect is dramatic even before reaching the horizon. There is a region near the black hole where light can orbit in perfect circles. If a photon enters that narrow band of space with the right direction, it will race around the black hole again and again, caught in a loop that is both straight and curved at once. The photon is not trapped by a force. It follows the straightest route through an extreme geometry where straightness itself curves inward. From a distant vantage, the photon seems to circle like a desperate swimmer caught in a whirlpool. But the whirlpool is geometry. The struggle is illusion. Closer still, the stretching of time becomes overwhelming. A distant observer sees each moment of your fall lengthen, movements slow, clocks crawl. A final signal from your vessel takes what appears to be eternity to reach her eyes. In her understanding, you never cross the boundary. The black hole steals your motion by bending the timeline itself. You cease to be part of her future, but your experience remains unchanged. You cross the horizon naturally, unaware of any barrier. Falling feels like drifting in calm waters. You shine your flashlight ahead, and the beam obeys your command. If you could observe your own clock compared to the clock outside, you would realize that the outside universe has sped forward. Entire ages could pass beyond the horizon, while you witness only a few seconds. The black hole does not slow your light, it slows your time. This difference in perception lies at the heart of every illusion we have encountered. When gravity is weak, the shifts in time and space are subtle and easy to ignore. When gravity is strong, the shifts become undeniable. At a black hole horizon, they become absolute. The universe does not allow time inside to match time outside. The two regions are separate realms with no shared rhythm. Light shows this separation with perfect clarity. A beam fired upward from the horizon is caught in endless climbing. The distant observer sees that climb stretch across infinite time. The photon has not changed speed. The meanings of distance and time have changed completely. And in that transformation, we see the most dramatic proof that constant speed shapes reality rather than yielding to it. Black holes teach us that the universe protects the speed of light by bending space and time to its will. They show us the limits of our perspective. They reveal that when we believe light slows or stops, we are trusting clocks that cannot survive the journey into deeper gravity. Light continues unbroken. We are the ones who lose the ability to keep up. The edge of a black hole is not the death of light. It is the death of an observer's ability to witness light escape. This is the ultimate demonstration of relativity. Motion is shaped by geometry. Perception is shaped by clocks. And every illusion that gravity creates is a window into the deepest truth of the cosmos. In the chapters ahead, we will explore what lies beyond our ability to measure. We will ask whether light experiences time at all, and what that means for a traveler that never stops moving. We will face the strange idea that while gravity slows time for massive objects, photons stand apart, untouched by the passage of moments. At the brink of the darkest realms, we learn that light does not hesitate. It is time that hesitates. Imagine you are a traveler moving faster and faster through space. As your speed increases, time for you begins to stretch. Moments lengthen. Clocks around you seem to tick slower and slower compared to the clocks left behind. This effect is tiny when your speed is slow and gentle when you ride a train or fly in an aircraft. But if you approach the speed of light, the stretching becomes dramatic. From the point of view of someone watching you from far away, your heartbeat slows to a crawl. Your seconds become long and lazy. And if you could ever reach the speed of light itself, the transformation would reach its end. Time would stop entirely for you. This is not merely a strange idea. It is a direct consequence of relativity. Time does not flow equally for everything in the universe. The faster you move through space, the slower you move through time. A photon moves through space at the ultimate speed. So what becomes of its time? A photon is a creature of pure motion. It is born in a burst of energy and instantly travels at the constant speed of light. There is no gradual acceleration. There is no delay. From its very creation, it occupies the limit that no massive object can ever reach. If time slows for a traveler approaching the speed of light, then for a traveler that actually reaches the speed of light, time no longer exists as a living rhythm. The universe does not allow a photon to experience a before or an after. It has no internal history. The photon does not age. Picture a photon leaving a distant star. The light may travel for what we call billions of years. It may cross the expanding voids between galaxies. It may push through clouds of gas and glide past worlds that are only beginning to form. When at long last, that ancient photon strikes your eye or your instrument, our clocks declare that an unimaginable expanse of time has passed. But for the photon, that journey contained no passage of time at all. In the photon experience, it was emitted and absorbed in the same single instant. No seconds, no years, no waiting, just motion. This sounds difficult because our senses teach us that time is universal. We remember yesterday and expect tomorrow. But photons do not remember and do not anticipate. They carry no inner life of duration. They simply exist along the edges of spacetime, where the meaning of time dissolves. The reason lies in relativity, deep structure. For objects with mass, there is a balance between movement through space and movement through time. When you stand still, you move entirely through time. When you move, some of that motion is spent traveling through space, and less is left for time. The faster you go, the less of your motion is devoted to time. A photon spends all of its motion on space. None is left for time. The photon is still part of space-time, but it occupies a path where time is a silent dimension. This does not mean photons are unaware. Awareness requires memory. Memory requires time. Light does not have time to keep memories. This does not make light alive or conscious. It simply means that when we ask what a photon experiences, the question loses meaning. Experience is change. Change requires moments. A photon has none. Yet this absence of time creates something extraordinary. Light links distant regions of the universe in ways no other traveler can. It takes no time from its own perspective to cross the cosmos, so it can connect events separated by billions of years in our measure. The first stars that ever shone sent photons that reach us now. For us, their journey lasted longer than the entire history of human life. For the photons, the emission and arrival are neighbors without separation. Even in the grip of gravity, this remains true. When a photon nears a massive object and time stretches, the stretching belongs to the observer with a clock. The photon itself does not slow. It does not feel the breaking of seconds. It rides through that region unburdened by the thickness of time that traps massive objects. When a distant scientist sees delay, the photon sees none. When a telescope witnesses hesitation, the photon remains unchanged. As gravity grows stronger, the difference becomes more extreme. Near the edge of a black hole, time nearly stops. For a massive object, this means motion toward the horizon appears to freeze. Light emitted upward struggles against the slowdown until it fades. But for the photon, time was already absent. The stretching affects only how the observer sees the photon, not how the photon exists. The photon has no personal timeline to distort. This is why we say that light never slows. It cannot slow because it has no internal flow of time to measure change. Its constant speed is not simply a physical rule. It is a consequence of its timeless nature. To slow down would require the ability to experience the rate of motion changing. A photon does not possess that ability. It never had a rate of time to begin with. We measure durations. We count seconds between events. We age. We remember. Light does none of these things. The heartbeat of a photon is frequency, not time. The beat defines the wave, but not the life of the traveler. That rhythm can shift when gravity reshapes time, but the photon does not feel that shift. The shift exists only in a comparison between one observer and another. The timelessness of light allows physics to remain grounded. If photons experience time, two events separated by light could disagree on which came first. That would ruin cause and effect. The universe protects causality by tying the passage of time to mass. What does not have mass does not carry a clock. Light, therefore, enforces the order of events. It defines what can influence what. It keeps history from turning in circles. We now see that the nature of light is deeper than speed. It is the messenger that travels through a structure where time bends and space curves. Yet light refuses to adopt the perspective of any single observer. It connects the universe across ages, without ever knowing that ages exist. Massive objects argue with gravity. They feel weight. They strain against the curvature of space-time. Light never argues. It embraces the geometry fully and is freed from the passing of moments. This is why the photon always remains true to its speed. Without time, speed is not a contest. It is simply the state of being. And now we stand at a horizon of thought. If photons do not experience time, then what slows down when gravity grows strong? If light does not age, what is aging near a black hole? The answers reveal the profound difference between what we observe and what truly exists. Gravity bends space. Gravity slows time. Light glides unchanged through the distortion. We misunderstand only because we insist on measuring light with clocks that the photon does not possess. The photon lives in motion alone. In the next chapter, we will turn this realization back toward ourselves. We will ask the question that gravity has forced upon us again and again. If light is constant, then what truly slows in the presence of gravity? The answer will complete the illusion and reveal the truth that has been waiting all along. From the first moment we learned that light slows when it passes through glass or water, we assumed that slowing is a natural and universal idea. We thought that when a photon has a longer journey, it must be moving more slowly. But relativity has shown us a different story. When gravity enters the picture, the illusion begins, and now the time has come to remove the illusion completely. Gravity does not touch the photon speed. Gravity touches time. Gravity touches space. It stretches and squeezes the stage upon which light travels. We misinterpret the performance because we trust our own clocks and our own rulers without question. We forget that gravity reshapes the tools of measurement, not the thing being measured. So the great question we must finally answer is simple but profound. What truly slows down in gravity? Imagine you are standing on Earth. Gravity pulls you toward the ground and keeps you from floating away. But the feeling of weight in your legs and feet is not caused by a force dragging downward. It is the ground pushing upward, resisting your natural curved path through space-time. You are not free to move with the geometry. You are being held still while your true trajectory tries to move inward. Weight is the tension between what space-time wants and what your body experiences. Now imagine you are in free fall. A spacecraft engines turn off and you float weightless. Gravity has not vanished. What vanished is the resistance to the curve. You feel nothing because you are finally moving according to the geometry. You and every photon near you share the same kind of motion. A photon never feels weight. A photon is always in free fall. It is never pushed or held back. It has no mass to resist the curve. It simply rides the shape of space-time perfectly. When we place a clock in a stronger gravitational field, the ticking slows, not because the machinery weakens, but because time itself stretches. A clock is a heartbeat. Its rhythm depends on the structure of space-time at its location. When gravity deepens, the clock heartbeat slows. When gravity weakens, the heartbeat speeds up. High above Earth, astronauts age slightly faster as the relentless pull beneath them weakens. On the ground, we age more slowly without ever noticing. Gravity touches time. Time responds to gravity. The photon passes through this changing flow without slowing. But if we compare the rhythm of the photon to the rhythm of two clocks in two different gravitational fields, we find disagreement. That disagreement is not the photon fault. It is the clock fault. The photon is always faithful to the universal rule. The clocks are faithful only to the gravity that shapes them. Light is constant. Clocks are variable. Where gravity is strong, the clock slows. Where gravity changes, the meaning of speed changes too. The illusion that light slows arises because we insist on using clocks that do not match one another. We are comparing different worlds while pretending they are the same. Now consider distance. If you lay out a ruler near a massive planet, the space between the marks stretches in a way that no eye can see. The ruler itself grows longer in the geometry of curved space. If a photon travels that distance, it covers more real space than we expect, even though each tick of its own local speed remains identical. If we measure that journey with a ruler calibrated in flat space, we will say the distance is shorter than it truly is. We combine the wrong distance with the wrong time and blame the photon for the result. Light reveals the truth only if we measure locally. Gravity reveals the illusion when we compare across space. So what slows down in gravity? Not the photon, not the motion. What slows is the ticking of clocks inside the gravitational well. What stretches is the map we use to measure distance. The photon remains unchanged while the universe shifts the meaning of its journey. We have been fooled because we trust our senses too easily. We look at a black hole and watch a photon freeze near the horizon. We say the photon has stopped. But time stopped, not motion. When we collapse under the impression that light has surrendered its speed, we are surrendering to the limitations of our own perspective. Our senses evolved to navigate a world where space-time curves gently. The ground feels flat and time feels uniform, but those feelings are illusions created by survival. The universe is a wider and deeper place than our instincts can imagine. Relativity lifts the veil and shows us that gravity changes the very fabric of reality. Space stretches, time slows, and light, the one constant, continues without hesitation. Once this truth settles in our minds, the mystery dissolves. Light never slows. The world around it changes shape. Those changes make speed appear different only because we insist on forcing a flat idea onto a curved universe. There is a quiet beauty in this realization. Light does not resist gravity. It does not fight the curve. It becomes the perfect traveler, always obeying the geometry that mass creates. We are the ones who misunderstand what we see. We place our confidence in tools that gravity constantly warps. Our rulers lie. Our seconds betray us. And our intuition struggles to follow the deeper truth. Everything we have learned to this point prepares us for a new way of thinking. Gravity does not act on light directly. Gravity acts on the arena where motion unfolds. Light simply moves through the arena unchanged. It reveals the shape of the stage. It never breaks character. It never doubts its speed. This chapter answers the question that haunted physicists in the early days of relativity. What slows down when gravity grows strong? Not light, not motion. It is time that slows. It is space that stretches. The photon moves unchanged through the illusion that gravity creates. And so we approach the final understanding of this journey. The speed of light is constant everywhere. What changes is reality itself. Light always follows the shape of space-time, but space-time is not flat, and we must learn to see that bend if we wish to truly know what the photon knows. In the final chapter, we will bring every piece together. We will see that the universe does not slow its fastest messenger. The universe instead slows us. Our clocks, our movements, our sense of order. Light is constant. We are the ones who change. From the beginning, physics has been a search for what changes and what does not. We have learned that objects can move at different speeds. We have learned that planets can spin and stars can erupt. We have learned that galaxies race away from each other as the universe grows. Through all of this motion, one rule has remained untouched. Light always moves at the same speed in a vacuum. That rule is the foundation upon which everything else rests. To protect that rule, the universe bends. It allows time to flow differently in different places. It allows distance to stretch and contract. It allows geometry to shift so completely that straight paths become curved. The photon never changes. Our understanding must. The constancy of light forces us to accept that space and time are not steady. They move and flex to keep the law of light intact. This is the heart of relativity. When gravity strengthens, clocks slow down. They slow not because something pushes against them, but because time itself thickens around mass. When time thickens, events unfold more slowly in that region. If we watch from far away, the delay appears to belong to the traveler, but the delay belongs to the clock. When a photon passes through stretched space, the journey appears longer. We say the light is slowed, but the journey belongs to the geometry. The speed does not change. Our planet provides a quiet demonstration of this truth every moment. A person standing on a mountain ages slightly faster than someone at sea level. At your feet, time passes a tiny bit more slowly than at your head. Every moment on Earth carries a gradient of time, invisible yet measurable. Satellites in orbit must adjust for this difference to guide us correctly. Even our ordinary world reveals that time is a river with shifting currents. Now imagine a star so massive that time near its surface drags heavily, like honey resisting a falling leaf. As light climbs out of that gravitational well, its wave crests stretch farther apart. Its color shifts into red. We might say the photon has lost energy, but what has truly changed is the flow of time against which we measure the heartbeat of the wave. Imagine space bent so strongly that a photon passing near a cluster of galaxies splits into multiple paths. Each path remains straight in its own curved region. The photon arrives from directions we never expected, and if those paths differ in how deeply they descend into curved space-time, the photons arrive at different times. The delay belongs to the route, not to the photon. Imagine the edge of a black hole where time nearly stops. A photon climbing out appears frozen from the perspective of someone far away. We might believe the photon has been captured, but captured is the wrong idea. It is time that slows to stillness. The photon moves exactly as the geometry allows. Once we truly grasp this idea, the world becomes more honest. There is no longer confusion about what slows and what moves. Distance and duration are not foundations, they are consequences. Mass and energy tells space-time how to curve. Space-time tells everything how to move. And light, with its constant speed, is the ruler by which the universe measures its own shape. Everything we observe about light in gravity points to one conclusion. Gravity does not slow light. Gravity reshapes reality. It stretches the road and alters the ticking of the clock. The photon continues without hesitation, but our understanding falters because we measure a curved world with flat expectations. Even the horizon of a black hole, the place where light cannot escape, is not a wall that slows light. It is a region where the idea of outward motion no longer exists. Time inside that horizon does not point outward. Every path points deeper into the collapse. Light moves with constant speed, but the direction that once led outward now leads inward. The photon is not imprisoned. The geometry has removed the exits. This is why we must shift our thinking. Instead of asking why light slows in gravity, we must ask what gravity does to time and space. Instead of imagining light struggling, we must imagine the universe redefining distance. Instead of blaming the photon for arriving late, we must see that clocks disagree on how late is late. The photon does not change, the viewer does. When you realize this, the cosmos gains clarity. The bending of starlight becomes a map of space-time. The delay of signals near our sun becomes a measurement of time slow. The redshift of photons climbing from stars becomes a fingerprint of gravity. The apparent freezing of light near a black hole becomes the final proof that time is flexible. The constancy of light reveals the flexibility of everything else. Light never slows, we slow. Light never hesitates, time hesitates. Light never changes its speed, space changes its length. Light remains the anchor while the shoreline of reality moves around it. This truth is simple but breathtaking. We are used to thinking of speed as the variable and space and time as the constants. Relativity teaches the opposite. Light is the constant. Time and space are variables, bending to preserve the rule that gives the universe its structure. And the rule is this: light moves fast, time moves slow. Gravity reshapes everything we see. In the end, it is not light that struggles against gravity. It is our perception, our clocks, our measurements, our assumptions. We feel the weight of space-time. Light does not. We age. Light does not. We are bound by the passage of moments. Light is not. It is the perfect traveler that connects what was to what will be without ever living through the in-between. This is the revelation that physics fought for more than a century to understand. Light never slows. We do.